you know, in my career, I started as a physician, and then I did molecular biology, and then I did computational biology. And so biology and computational biology and sequencing and all that stuff is kind of like, the thought process is, let's do an experiment, let's gather meaningful, high quality data, and let's figure out what's going on, okay? And then you go over to the other end of the spectrum, and that's clinical research, and you can't do that. And if you try to do that, like in a company, they hurt you. They're saying, hey, you are violating SOPs. You can't do that. You have to have a hypothesis, and you have to test it, and everything, the generation of the data for the hypothesis and the testing and the method and everything has to be pre-arranged. So the world is completely upside down. Once you are in the experiment, you can't touch it anymore. You can't change it and saying, wait a minute, we forgot to look at this. Can't do that, okay? And so having done this for a while now, I'm completely used to both ways of thinking. The reason I'm bringing this up is because we are a little bit in this game here too. You're going to see it in a second. So that's why I wanted to first explain a little bit OHDSI and how it works and how these people think and what they do. And then what happened when we started bringing in genomic just variants in principle, not just genomic variants, molecular variants as entities that need to be studied. And the way the thinking and the thought process defines how we approach this from another end and what our problems are. And so you're gonna see it in a second. All right, meeting is being recorded. Yes, and now I have to. And so we're not a ton of people here, right? We have 3 people or something like this, 4. So please just make this a dialogue or a conversation rather than a very top-down presentation. Share screen. I guess just screen 1. See this?
Yep, we see it.
Okay. Oh, but if I go on full mode, then it probably jumps in the wrong screen. Yes, it does. And then there's a way to stop that.
You should be able to do it at the top of a page.
Top of the page.
Probably where it says display settings. I think that drop down lets you swap them. There we go.
Right.
Good. Perfect. I learned something. So OHDSI. What the hell is OHDSI? What does it mean, OHDSI? Why is this called OHDSI? Actually, the reason it's called OHDSI and not ODYSSEY, which kind of like was the idea to call it Odyssey, like Odysseus after the Trojan War, is that at the time when this thing was pulled off, if you're trying to get the website odyssey.com or odyssey.org, you have to pay a lot of money to some squatter. So OHDSI was a 5-letter available domain name, and so retroactively it became observational health data science and informatics, and other people made it to Open Health Data Science Initiative. So there are different names for what the acronym is supposed to mean, but really the thing is it's an odyssey. So it takes a while to solve the problem. What's the problem that it's trying to solve? Let's take this thing away here. Otherwise we see ourselves all the time. No. It's getting worse. Why? I thought this little beast here makes it small. Oh, here you go. Okay. Empower a community to collaboratively generate evidence that promotes better health decisions and better care. So essentially it's an open community that works collaboratively. Why does it work collaboratively? Because this type of research is really hard to do alone. Because what you need to do is you need to have data. I'm going to say what it is in a minute. You need to have data. You need to have people who know how to manipulate the data. You need to and data can't flow easily like in more biological research, because it's patient data. So there's a whole lot of restrictions. And you need clinical researchers who know what the questions are and how to address them. And you need statisticians who know how to do this from a statistical perspective and get the right answers. And you need like informatics people who can deal with large data and all that kind of stuff. So no institution, or very few institutions, have all of this under one roof. So you need a community to come together, okay? And there's a reason. There's a predecessor project called OMOP that started the whole thing, and it was started by the industry and the FDA. Long story, but in 2014, OHDSI was born, and it's an open initiative. And it has, these values, which means, let's fix the problem. Problem being, we really don't know very well for healthcare interventions, what works and what doesn't work, okay? So we don't know for all the drugs, all the outcomes, at least the public doesn't know. We don't know all the other interventions that are not drugs and their outcomes. We don't know the risks. We don't, and this is, when we do this, we don't know the cost. We don't know the effectiveness of things. The whole healthcare industry is way behind all other industries in the ability to get really data-driven hard facts on what's going on, okay? And so that's what we need to fix. We need some innovation because the current methods don't scale. We need to have reproducibility. We have a big reproducibility problem. There's a lot of studies which contradict each other, or they're just plain non-informative. Again, we need the community that needs to be open to the community, so people actually can exchange with their assets and their abilities, so you can together come to a solution. Need to be able to collaborate, needs to be open. Why does it need to be open? It's like encryption tools. The ones which are most trusted are the ones in the open domain, because you know that the government hasn't built in a backdoor. So same thing here, make methods open instead of black box, somebody's proprietary commercial or academic environment. Beneficence, make sure that this is for the greater good and not just for the for some commercial success. So that's what this thing is. It's really very loose and collaborative. There's a coordinating center at Columbia University, Biomedical Informatics Department. But really that thing, what it does is it organizes symposia and hackathons and runs a website. Most of the actual work happens by people just coming together loosely in a collaborative fashion. They all have day jobs. And so it's a journey. You have patient level data and you need evidence. It's about populations. We are not treating patients, individual patients. It's about populations, what's going on, what works, what doesn't work. Okay. And how do you want attributes to be? What's a reliable evidence? Why isn't that obvious? Well, it has to be repeatable, which means you should be able to do exactly the same experiment, same question, same researcher, same data, same analysis, same result. Reproducible, somebody else repeats it. Replicable, same question, same analysis, similar data, researchers undefined. Generalizable, different type of data get you a consistent answer. Okay. Robust, different analyses, no matter how you ask the question, get robust answers. And then we introduced the term calibrated, which means similar questions, if they are applied to the same, by the same researcher, to the same data in the same method, should give consistent results. You guys, for you, this is probably absurd, but this community does not use positive negative controls for what they are doing. Okay, this is very disturbing. To them, it's the other way around. It's, what do you mean control? What's a control? Well, if I run a study to test the effect of a certain drug, let's say a COVID vaccine, whether or not it creates, a transverse myelitis in the spine. Well, you would want to also run a drug where you know that it causes it, and you would want to run a drug where you know it doesn't cause it, so that you can at least prove that your method is robust and works. Right? So the negative controls doesn't produce a signal. The positive control shows it does. It's not happening. Okay. So it's not the standard paper. You can run a paper. Most epidemiological papers are written with completely in the absence of controls. That's just one example of things where we as a community just want to lift the whole level of how this is done in order to improve the quality and have higher impact. Also, lift the scale. This needs to happen. This whole thing, one PhD student, one disease, one drug, one outcome kind of thing. It's crazy, but that's how traditional epidemiology works. It's very reductionist, and of course, you see it today in COVID has brought this all to the attention of the world. The whole world now looks at how epidemiology gets done and how awkward it is, and how these pieces of evidence contradict each other, and they are based on insufficient methods, and the methods can't even say how good they are. They can't even say, you know what, I have a strong belief or not so strong belief about what I'm about to tell you. Even that we can't say. Right? So there's a lot of problems which need to be solved. Oops, I'm gonna, yeah, no, it's fine. It's an international thing. There's a lot of traction. When this started, and I was at the beginning, I was pretty scared. I thought it's an open source thing with no financing, no money, no funding, zero. How can that ever work? Okay, nobody's going to do anything. I mean, I can't just do it all myself and all the other three guys here. I was so wrong. Lots of people all over the world, lots of study, lots of activity, huge symposia. I didn't know that. I just didn't know how open communities work and how you can switch this thing on and they come. The fact that there is no money, and I'm going to stop in a minute and talk about what we actually need to talk. The fact that there's no money turned out to be, again, completely counterintuitive to me, turned out to be a blessing. If you have a community and there's no money, or you have an initiative and there's no money, a whole lot of people don't show up who will otherwise waste your time, who are only there for the money, to sit in the governance committees and create a whole lot of empty activity, when in fact all they want is money or the reputation or the visibility. This thing doesn't have these people. They don't show up. They don't exist. You have only a bunch of geeks who are really love to. And they actually, it's the opposite problem, right? It's really a lack of process and organization sometimes when you do need it, which hurts it, because the people they're really all hands-on. They love to play with the Lego bricks. Okay. So a lot. A lot of activity, a lot of data in different countries, lots of patients, a lot of records. We thought that at the beginning, we're going to put out a goal of having 1 billion patient records. That wasn't a problem. I thought this was going to take like 10 years, at least 15 years. That came together very quickly. Patients are not all non-overlapping. Some of them are overlapping. So if you take out the overlap, then it probably shrinks by a factor of 50%. But still, I didn't think that this problem is going to be so easy to solve. And the other problems are much harder to solve. Here's how it works. It works by leaving the data, like many of these people are data, but some of them are researchers without data, but lots of them have data. You leave them in place. You don't merge them. Obviously, you can't put them into the public. That is a huge impediment for this type of research. Because usually the organizations stick to the data, nobody else can see them, you can't reproduce, you can't see anything what happens. How do you get the large numbers? How do you get to 2.7 billion? Okay, by harmonizing them to a standard model. So everybody has to convert the data to a standard model. It's quite an investment, but once you have it, you can do federated queries and research. So you can send out the same query, the same code, same R package to all of these people and say, run it. And if they've done the standardization right, the answer is correct. Okay. So lots of people saying, oh, you can do this. How can you do this? You can't, like, it's like all different institutions, they all have different database models. Yes, you can, because it's all the same thing, right? Patients have a problem, go to the doctor, get diagnosed, get treatments, get drugs, get surgeries. They're better, then they usually don't show up anymore, just drop out of the data. Or they don't go, then they come back. Okay, it's the same thing all over the world. Yes, you can harmonize it. It's actually not that hard. But again, the community, there's their work group which maintains the data model. And with the harmonization, that you also need to harmonize is the content. That's actually harder, because all the countries, they tend to represent their stuff in different ways. It's all heavily coded. The reason it's coded is because these systems, because the healthcare systems work, the way they treat their data is for two purposes. One is in order to just have a record of what happened to the patient. It's called EHR, electronic health record. And the other thing is to create an invoice to the insurance. And in order for that to happen, they are standards. Standards is a strong word, but there's somewhat of weak standard. Every country has their own. Some of them are global. Many of them are not global. But at least some of them are local to an institution. But there's some hope. So in principle, people understand that the facts have to be encoded. They have to be normalized. So COVID-19 is a concept, has one ID. If some patient got diagnosed today with COVID ID, then the record will contain patient ID and the diagnosis code of COVID-19. And if you have that harmonized, then you can do truly federated research. You never get access to the patient data. You just send in the analytical package into the institution. They run it, give the result back. The result is an aggregate summary. There's no problem with patient identification or anything like that. That's the idea. That's the magic. There's a lot of work to maintain that, okay? Because you have all sorts of different entities that you have to harmonize. The diagnoses, the treatments, the symptoms, then the drugs, then the procedures, then the devices, then visits, hospital and ER and what have you, doctor's offices, insurance stuff, just payers, other healthcare entities. So there's a whole lot of stuff that you need to harmonize. But it's bad, but there are a few which are really key. And the key ones that you really need are conditions, drugs, procedures, devices and visits. If you have those, you can participate in most studies. Okay. This is the slide which I should have said this. So essentially, what the OHDSI does is it maintains this large repository of different existing standards or non-existing standards, local coding systems, and maps them to a standard. So you have one way to say COVID, one way to say heart attack, one way to say I don't know, prostate cancer. Okay. They're also in a hierarchy, so you can say things, give me all cancers, or you can give me all lung cancers, or give me all non-small cell lung cancers, give me all lung cancers that are metastatic. So, you know what I'm saying? So you can actually, because it's hierarchical, it's much easier to, it's actually possible in certain ways to select a population, even though the individual diagnosis could be incredibly complicated and detailed. But you don't care about the individual detailed, you just want all lung cancers. Okay? So that's the idea. That's what this does. And this is done centrally at the level of the initiative. So here's, as I said, here you have 3 databases, like one institution, second institution, third institution. This is their model. You transform them to the OMAP common data model. OMAP is a predecessor organization. When the model is still called OMAP, we never changed the name. And voila, it looks exactly the same. And then you can run standardized open source analytical code. Okay. And you create open evidence. These guys have to be private. This can be in the public domain. So whatever OHDSI does, it's all on the website and in public for free or Apache public license. So commercial entities can use it if they want to, but you know, there's no strings attached. What kind of evidence do you generate? So I have to talk about this real quick. Look at the time here, 1:30, it's not that bad. What kind of evidence does this stuff, what is this about? What is this clinical research, what type of evidence does it generate? It's, oops, this is the wrong slide. It's actually in the COVID-19, there was a huge, people came together and did so there was in March, there was supposed to be a European symposium. And of course that fell through because of COVID. So people said, we're going to do a gigantic COVID experiment and ask a whole lot of questions across the world. Everybody was like energetic. Turns out that it did happen. At the beginning, the interesting dynamics, again, that was, I learned this on the way. At the beginning of, in March, there was suddenly a rush to find out things about COVID. So everybody jumped as fast as they could and, inundated the journals with papers. Lots of papers, low quality. And we don't want to do low quality. We never do quality. We have everything, it's in a network, lots of people. We have to wait till the whole network is, up to speed. And, they have to run it. And they, the vocabularies had to be fixed for the COVID and all of that stuff. So we were small, slow, and robust. In this drama mode, no, people weren't actually looking for that, and it was just a race, a crazy race. Turns out a lot of it's like the famous Surgisphere scandal, of course, happened. So some people went way too far on the other end. So now we are in the mode where things are a little bit more relaxed and people actually take care of things and look for quality and do checks and so on. But for the community like this isn't the fastest thing. If you're just a institution with name recognition and you just take your data that you have and just push something out, then you're going to be the first one and you're going to get a big paper. That's what happened here. It was a little frustrating to some people. Well, I'm not really an academic, so I could watch this from the side. But it was also interesting how the community and how research works under that kind of a pressure, contrast to what it usually does. Anyway, So these are the institutions which participated, again, all over the world, numbers of patients. And what they did is, and I'm not going to show you everything, but I'm going to use this as an example to show what kind of things get actually studied. 3 things: characterization, prediction, patient level prediction, population level estimation, effect estimation. Okay, these are the 3 things. So the first one is what happened to patients who have COVID. You know, how many of them go into the hospital, how many of them get into the ICU, how many of them get ventilated, how many of them die. Okay, what do they take? Is there, you know, how many of them had prior disease X, Y, and Z? Things like this, a lot of that. Patient level prediction means, given all the facts that I know, a patient who develops COVID on day 1, can I predict what's going to happen? Okay. And then, oh, and again, this is COVID, but of course this is standard, right? This is all over the place, right? Can I predict what I don't know either yet, or what I don't know because I can't see it, I can't ask it, right? So for example, certain rare diseases, can I use this inference model to find rare, hard to diagnose disease. So prediction doesn't always mean in the future, could be in the present. You just don't see it. And then population level estimation is the prediction uses all the facts that you have, all the factors, and then the model picks the factors that are predictive for each patient, one patient at a time, right? And this one does a whole lot of patients, but just one factor, okay? The effect of drug X, okay, on the progression of COVID. Okay, what does it, how does it change your odds to get ventilated, die, whatever, right? How does it change your odds to have a side effect? For a population, not for an individual. Individual could have a higher or lower chance or ratio, odds ratio, whatever it is that you're measuring. But in the population, you're leveling, you're doing. So this is estimate the effect of one factor in lots of people, and this is effect of all of factors in one person. Okay, and this is just characterized. Tell me what's going on. So that's what happens. These are the things which this stuff, which is the research community does, and so COVID is no exception. It's the same thing. So here's a characterization job, big time at the beginning. Patients hospitalized with COVID are systematically different from those hospitalized with flu. So at the beginning was, you know, everybody said, well, it's just a flu, right? Is it just a flu or not? So paper came out, Nature. And then here's, I'm not going to go into this, but these are the different institutions. These are the conditions. This is the medications that people use. And it's like one way to see, you know, how much variability there is in where you see effects that are interesting, right? So I don't know. Here, there's a lot of this medication. There's a significant difference in the prevalence compared to the comparator flu.
Can I ask a question?
Yeah, please.
So if you go to the previous slide, I'm just curious. No, next one, please. Yep, this one. So I'm just curious. One thing I was looking for, did you folks try to add the parameter would describe the health status of a patient? Because one of the problem is, for example, when people looking at COVID-19 and cancer patients, one of the complicating factors seems to be the health status of a patient.
Okay.
And I'm just curious, have you tried to incorporate that somehow?
Yeah, so this is the health status, right? These are all pre-existing conditions. Here you go.
Right, but what I'm trying to say is, For example, you may have a patient which have blood cancer.
Yeah.
And they even have maybe both recurrence, but they could be quite different because, for example, one of them is 53 years old, has reasonable weight, has reasonable lung function, and another one, let's say 59 years old, and that patient can barely move outside the house. So technically you could assess lung function, you could assess other things, but somehow these basic metrics often get lost.
Yeah. So the way this is actually then the prediction, right? So what you want to know is can you predict a certain outcome, like a bad outcome? In this case, hospitalization, in intensive services, death. So a prediction job usually in logistic regression or something like this. What it does is it takes all features, which means all known diseases from before, all known age, of course, and gender, all that kind of stuff, all known drugs, all known procedures, and then put it in a pot and boil it and see which of them are going to predict your outcome, right? And so that's what it is. And so, the method will come with a prediction, and you can calibrate how good the prediction is in, how often it takes for each patient. You'll see what actually happened to the patient was predicted, and then you can calibrate this. In this particular case, it was shrunk to only the important ones, and we know this, right? So it's cancer, lung disease, obstructive lung disease, diabetes, heart disease, hypertension, hyperlipidemia, and kidney disease. These are the predictors. If you have any of these, then your likelihood goes up for these bad outcomes. The older you are, I mean, we all know this right now, right? With gazillion times in the media, men worse than women. So what we did is we took one of these. So that was data driven. The data created the individual factors and extracted the ones which are relevant. And so the way you do that is you can do this on a little graph like this. You type in whether or not you have it, and then how old you are, and then whether you're male or female, you get a score. You put the score in here, and you get a predicted risk. Right? And this shows you the actual patient which contributed, for whom the model actually calculated this, right? Who predicted to this scale. Okay, so that's how that's what a prediction then does. You have your pre-existing facts and features, and you're looking whether or not you can say what happens in the future, or what already happens now, but usually it's future. Okay. Does it explain this again?
Yeah, I mean, one of the complication, I guess, what I was trying to refer to, if you, for example, put patient into the slices, let's say the same age group, and they have the same cancer, and other things on what you have on your screen sort of the same, they still have huge variability in responses.
Yeah.
Now, you can decrease this variability if you limit to the same country or to the same level of medical care, but even after you do that, variability is huge. And what I see anecdotally from the oncologists, what one of the big difference is the health status of a patient, of actual metrics, how physically fit is the patient. That information, in most cases, is not captured. But what I heard anecdotally, it made huge difference in patient survival.
There's a lot of facts which are used like intuitively in day-to-day patient care, which are not systematically captured. That's absolutely correct. And general, level of fitness of a patient is usually, there are scores, but they're not typically collected easily. So that's correct. So we are working on, so these prediction models, they have to figure it out, but maybe the other diseases or the other interventions will be a surrogate marker for the thing that you had in mind. So that's the hope, right? I don't have a score for fitness, but I see what's going on with the patient, or well, the model sees it, right? It sees that, I don't know, nursing, right? And infusions, and, that kind of thing, UTIs, urinary tract infections, right? For patients who are in bed, things like, fracture of the hip, that's for old people who are frail. If you have 2 fractures of the hip, then the model will figure out these are the frail ones because I can see the outcomes, So the hope is that actually there is let me go back forward here real quick. This is what it looks like, right? You have for each, you have many patients, millions, tens of thousands, hundreds of thousands, millions of patients, and you have lots of features, 150,000 features in a typical of these experiments, okay? Did you have a hip fracture in the last year or not? That's one of them. And they're very, very sparse. Most of them are just binaries. Sometimes you get you get little more than binary. Very, very sparse matrices. And then you hope that if you don't have, you just don't know, right? This feature, you don't have it. It's either because it's not captured or the patient didn't have it. You don't know that, right? But you hope that because you have so many, and it's a multivariate model, of course, but the other guys are somehow going to vote for you anyway. Okay, this is the challenge of this whole line of research. You guys have a different challenge. This is what they have. That these matrices are extremely sparse and the features are very highly correlated, awfully correlated to each other. If you have diabetes, you have cardiovascular disease, right? Almost always. So that's how that's the challenge to the analytical methods that they have. Yep, it's a lack of of facts. You can't rely. So the way observational data usually work, if something happens, you get a record, right? You have a heart attack, then yeah, you have a record in your health in your file, right? If you have cancer, you have a record in your file. So people assume unspokenly, make 2 assumptions. One is if you had something, it's in there. And if nothing is in there, you didn't have it. So type 1, type 2 error. Both of them are bad. Yes, if you have a heart attack, it's in the record pretty much, 100% almost. But scratch on your back is almost never in there. And all the other diseases are in the middle. Right? They get captured or don't get captured. Patient didn't go to the doctor, or the doctor is a different doctor, a different specialty, didn't find it important. Who knows? Right? So you have a recall precision, which is very different for the different features. And your methods have to deal with that. You still have to get the right out. You have to be able to read out the right effect. So the only way to deal with that, of course, is large numbers. Do lots of features, and don't be shy. Throw the kitchen sink at the method, and lots of patients, which is why you need a large network, because no institutions, institutions are finite in their size. All right, I need to speed up now, otherwise, oh God, I'm just talking about OHDSI and not about the genomics. I'm going to speed up now. Okay, estimation is measure the effect of one factor in a whole population. For example, hydroxychloroquine, the president was saying this is a good drug. Is it a good drug or not? And does it have side effects or not? What you do is you take a ton of patients who took it, take a ton of patients, you compare it to took something else, and then you do the statistics. And then you have at least something that you can bank on. There are all sorts of methods who do this, and they're all in the library and they're on GitHub in R, or it's all R-based community. The data and SQL and databases, the methods are in R, and they can all download them, and they depend on each other. So these are the foundational, and these are the ones which are typical methods for epidemiological research. Now, genomics. So this community wants to use genomics for what? For the same three things: characterization, prediction, and estimation. Okay. Obviously, you can't. A genomic variant is not an intervention that a human can decide to put in, so that goes away. But of course, the markers will have a huge effect that will contribute to some intervention. And of course, you want to characterize what it is. So people in cancer, you can't live without genomics anymore. It goes increasingly becomes a community which defines its the diseases and the interventions all through genomic markers. So we needed to bring it in. Okay. So how do these markers work in? So first of all, it started with tumor. There are other use cases which are rare diseases, syndromic diseases. Right now, that there's not a lot of activity there going on there. Cancer gets all the attention, and it has all the money and all that stuff. We know this. So it's tumor markers that we're talking about, and that's where it started. How do they use? Are they used in the clinic to screen, to diagnose, to stage? But the stage again is part of the diagnosis. And you do that in order to determine prognosis, to choose the treatment, and to monitor success, right? These are the very early classic ones, and this is the work. So a clinician, this is how the clinician thinks about genomics. Okay, there's a marker, there's a drug that you can use to hit it because this has some carcinogenic effect. These markers are only relevant in certain tumor sites. In others, they're not relevant. We know that. They're trying to figure out and create these guidelines, which are logical decision matrices of, if this, then that. And then they try to get to the FDA and say to the FDA, this is the right thing to do. So this is how this works. This is the world of the clinical researcher, how they see genomics. So there are these markers. They're coming from somewhere. They're coming from people like you guys. And the way you guys produce them is essentially bottom up. You run an experiment, you compare tumor to normal or something, and or you just take tumor and compare it to the reference genome, and you take what it is, and I just copied and pasted one of these typical chevrons here, and you create the cDNA, and then you sequence it, and then you get a whole lot of sequence information, and you do some bioinformatics in order to make sense of it and kind of like condense it to the actual facts. And so all variants are in play, are game, right? Usually we have 30K variants between any of us, if I remember correctly. Most of them means nothing from a disease perspective. They're just random stuff, random noise. The rest have potential change, either the protein level or the regulation level. But which ones and how many depends on how stringent your bioinformatics pipeline is, what kind of filter you apply, okay? For the clinicians, this is like absolutely crazy. You can't think that way. What do you mean? The bioinformatics decides what's important? How does that work? Which one is okay? So there's no definite list or has it or doesn't have it, but that's how they think. Means you take a bunch of symptoms, a bunch of lab tests, you run them all through, and then you know your answer. That's the thinking. That's the mental model. This doesn't work for them. it doesn't work for the OHDSI methods, because the methods need to have all these variants already in the system, so you can standardize them and you can put them into a feature and you can run your characterization, prediction, or estimation. So, and I explained to you already why. This is how it works, right? So you create this. This is what these guys call an analytical data set, and this is then they throw that through the statistics in order to create a hypothesis rejection or not. And so then we sat down and said, all right, let's try. Okay, let's try to create a set of variants that we could put into the existing machinery. The machinery is very developed. It's very powerful. It can deal with a whole lot of statistical issues, and the fact that it's sparse, and the fact that it needs big numbers, and there are people who are working on making it computationally much, speeding it up and so on. So what do we need? So we looked into, and my slide decks are a lot less elegant here now, looked into what people put together, right? So looked into these guidelines, into pathology checklists, all those kind of things. What do we need? What do they have? What do they work with, right? So they work with a bunch of variants on the gene level, karyotype level, microsatellite stability, histone methylation stuff. This, of course, this and this is the bulk. By far, on the genome level, there are either SNPs or there are mutations of unclear exactly where, or there are rearrangements, even less clear, or there are fusions. Or there's, polysomy or aneuploidy. On the transcript level, it's amplification, or not, the opposite, and the same SNPs, of course, they get passed through here, right? And the proteins, again, the SNPs are passed through, and there's expression level. This is the world, right? P53 high expression, cancer, okay? So this is, so we decided, all right, we're gonna need this. Where do we get them from? Give me a list of all variants that are relevant to cancer, and only those, not all the junk that's in the genome of anybody, of everybody. Can you give that to me? And then we turn them into standards in the vocabulary, and then everybody has to pick for P53 overexpression. They're going to have to pick this particular standard, and that becomes a feature, and then everything else works. We are good. We are happy where we always want to be, in our comfort zone. Okay. So what did we do? We went to collections that have these and said, we're going to bring in these collections. So here are the collections: CAP, CGI, CIVIC, ClinVar, JAX, LOINC, NCI, Thesaurus, OncoKB, and OncoPain is actually, this is a panel that's very popular in Korea. Okay. So we said, these guys, it's their job to create a curated list of genes or variants, variants which are involved in clinical oncology. Okay, if we have this list, we're gonna be fine.
Christian.
How do we do this? They're overlapping. Well, these guys here, you just by hand, the karyotypes, they're not that many. You can deal with this by hand. The problem are the SNPs. How do we put the SNPs together? Well, we unify on gene, on reference sequence, on coordinate and mutation. If they fit, one entry in CAP and one entry in CVI, then voila, it's the same thing. We consolidate it into one concept, okay? And that concept is going to be in our repository. And so we said, that's what we're going to do. We're going to, let's see, we're going to take the HDVS mutation, and it has everything we need in there. And we do it at the genome level and at the transcript level and the protein level separately, because they're different sequences. And yes, we know that one is, dependent, one is connected to the other. So we can also preserve these connections. But we do it at all three levels separately. And of course, in the genome, you have the chromosome then and that you use. So that was our naive approach. And I was very naive and it didn't work. What happened is genes are fairly okay. That the community, we have the Hugo list and it's okay. We are good. Sometimes they use old-fashioned names and then you have to figure out what it's called now. And sometimes they use they use one name for like a whole bunch of them, 1, 2, 3, 4, 5. They're actually 5 different genes for very related, but they're very related, so they don't. But overall, gene is okay. Reference sequence is a fiasco. Our community doesn't know how to convert one reference sequence to another one, right? And one is from NCBI, and the other one is from Ensemble, and the third one is LRG, and you have all these different. And then inside each of these databases, that's like, there are versions and there are measured or observed, and then those that they are created programmatically. This is awful. Okay, I have no way to understand. And then there are splice variants. And then I don't even know what I do with the splice variant. Is it still the same thing or not? Maybe it is, maybe it's not, right? Sometimes the splice variant cuts this thing in half and a certain mutation isn't even on there anymore. So now what do I do, right? Then there's a coordinate that's pretty okay within a reference sequence. It's okay. And then what the mutation actually is. C is replaced by T. There's a del, whatever, right? So what we said is, you know what? So this is something there's no way we can do this quickly. There are lots of bioinformaticians who build tools for this forever. And at some point, we're going to need this and we're going to talk to them and they're going to help us. But right now, how about this? We just take the gene, that is clean. Take the coordinate, that's clean. Take the mutation, that's clean. If they match, the likelihood that there are 2 different reference sequences that are different, and the coordinate, the mutation just happens to be the same, but actually it's different, is very low. We're going to bite the bullet. Okay? And we are declare, no matter what the reference sequence is, if 1, 3, and 4 is identical, we assume this is the same thing. We know we sometimes are going to be, in rare cases, we're going to be wrong. In most cases, we aren't going to be wrong. And we consolidate into a single representation. Remember, we need one single representation. We can't have 5 different representations. Then you can't do remote querying anymore. You need for one variant, one representation that everybody uses, one number. Okay. So we did this. We said, okay, good. People like Alex and Sergey and Peter, they're all going to complain if we do this because true bioinformaticians, they will look down on this. But for us, it's version 1. It's good enough. Let's just get going. Okay, let's get research going instead of just perfecting the substrate, knowing that we're going to have to deal with this later. So we thought, okay, let's have these guys. This is what the numbers are. So the first thing is that got us completely disgusted is that these numbers are vastly different, right? So ClinVar, everything that somebody submits goes in 500,000, and that's only somatic mutations. If you go germline, it's like 10 times as many. And so, OncoKB, it's 5,000. NCI, it's National Cancer Institute, they're 500. That's all they think it's important. The rest is not important. Loink in the similar area.
Can I ask you a question?
No, yeah.
So the thing is probably going on from everyone's mind listening right now. These databases are not put on the principle that they contain all the relevant variants. They are put on principle what variants have been submitted and what variants, for example, have been interpreted. Mm-hmm. So correct. You cannot assume in any shape or form that this represent all relevant variants.
That's correct. You got it. We can't assume this is perfect and it contains them all. And the opposite, we can't assume that is clean and it doesn't have a lot of junk. Of course, I mean 500,000. I don't believe so. But maybe it is 500,000 and they miraculously happen to get them all. But I don't think so, given the way how they collected. So we have this problem. So we thought naively, very naively, this is more mature. And there's a whole lot of very well established variants that people know of, and they exist and they happen, and you see them at a certain probability in these cancers. So what it looks like in reality is like this. Okay, so it's very small. I didn't have time to make a really nice, but it looks like. But the thing is, the overlap is very low. So most of the ClinVar don't have anybody else has that thing. Most of JAKs, nobody else has it. ClinVar and JAKs, they're the big ones, they share the most. Okay. OncoPanel, they have 5,000 that neither ClinVar nor JAKs, even though they're huge, have. Not one. Can you believe it? Some of them do overlap, right? So if you go to the OncoPanel here, 199, JAKs has them too. So this is not mature. These are the overlap is so much smaller. The intersection is so much smaller than the union. What does it do to us? Do we need a lot? Do we need a little? If we do a lot, we actually don't care that much. So questions, why don't we just throw in all the 500,000 ClinVars and all of them? Well, it's just a whole goddamn union. Just throw it in, who cares? Well, it's a little bit of a problem because you need to be able to actually browse and search in these. And if there are too many, then the browser and the search engine, they become very, not only slow, it's also very difficult then to find anything. And then you need very sophisticated ones. You can't just go by a simple name, but that's what the community uses, right? Diseases you just find by name. There's no other way to find a disease. So that's what happened here. So we are in this funny conundrum that problem number one is it's really hard to consolidate them. Somebody needs to help us with this stuff. And even the mutation, there are also things like, if you have two SNPs next to each other, you could also declare it as a whole sequence exchange. So there are things which are unambiguous, which are probably easier to solve. Reference sequence is not so easy to solve. And then the second problem is that the space is so sparse, and we don't really have what we otherwise would need, a repository of the things that are relevant. And so, of course, most people who are in your business, they tell us, well, that's not how you do it. You just measure and then you deal with what comes out. And we say, well, we don't want to do it that way. We want to do it that way. We know how to work. So we are putting a square peg in a round hole or something like this. This is a little bit what happened here.
Christian, I just want to point out that we're 5 minutes past the hour.
We're done. I have no more slides. No more slides.
Okay, cool. This is, so we understand, we found the same about the sparsity and non-overlap variants across these knowledge bases. I think Dimitri raised a really great point, which is that, these knowledge bases do describe very different types of evidence that have very different degrees of relevance to the cancer community. And that explains a lot of the order of magnitude changes you're seeing, right? So, if you have a big repository like ClinVar where people can just dump anything, you're going to get a lot of noise. If you got something like OncoKB, you saw like 5,600 there. They're actually several orders of magnitude lower if you're looking just at, like clinical interpretations, clinical biomarkers. They also have biological biomarkers, which are just, this variant is considered to be likely oncogenic for this gene. And that constitutes the vast majority of that, like 5,600 or whatever. And so depending on the type of evidence associated with these variants, that's another layer of complexity to consider. So that said, I think that there's, in the interest of letting people go to their subsequent meetings, maybe we'll pick this up next time.
Okay.
but it was this is a really great overview of OHDSI. I learned a lot about the organization and the sort of the mindset and sort of purpose behind what you're trying to achieve here, which I think was very helpful. And maybe next time we could talk a little bit about you know, the MetaKB, what it is, how it aligns with the work you're doing here. And it might help to like try to help the OHDSI community kind of standardize on a set of relevant concepts.
Cool, we'll do that.
All right, thank you everyone for your time today. Thank you very much, Christian, for presenting and introducing us to the project. I really enjoyed the presentation, and we'll see everyone again next time.
Good ones.
Thank you.
Thanks,
Thanks.
guys.
Bye.